Welcome to Coding Journey. Today I'm going to show you a DP solution to the problem jump to Sibling from CodeChef. So the problem statement is given as such. We are given an array, okay, and we are initially at this position, the first index, and from here we need to reach the last index, that is the nth index, and we can only make two jumps from any given index I. So we have two jumps, jump 1 and jump 2, okay, and using these two jumps we need to reach n from 1 in minimum number of steps. So the goal is to reach to n in minimum steps. Okay, so now let's see what jump 1 and jump 2 is. So jump 1 is basically, if you are at index I, you can go to next immediate index j, where ai and aj have same parity, where ai is nothing but the element at ith position and aj is nothing but element at jth position. And jump 2 means is that if you are at ith position, you can go to next immediate j if ai and aj have different parity. So same parity as in if both ai and aj should be having either, both of them either are even or odd, and in this case it would be even odd or odd even. So for example, let's say an example, this is the array, we are at this position, these are the indices, okay, so we are at position 1 and the next immediate index where we would have same parity is this guy, because this is even and this is also even, the next immediate even guy. So for this the same parity index would be 4, and for this only the different parity index would be the next immediate guy, which is odd. This is even, so we need odd guy. So this is the guy, and whose index is 2. So for this thing, the information is that the same parity index is at 4, the next immediate, and the different parity index is at 2, which is the next immediate. Okay, so now let's go to the solution. Okay, so as we saw here that we somehow need this S and D for every index. So then only we can start our DP approach. So for finding this S and D for every index, we need to do some pre-processing. So let's consider the same example. This is the array given. Okay, so for this guy we need to know what S is and what D is, where S is nothing but the same parity index and D is nothing but a different parity index, and of course it should be the immediate one. So but how do we do it? I mean, we cannot traverse it from here because it would just increase the time complexity. So what we could do is, instead of going from left to right, we would go from right to left. So we are at this position here. S and D doesn't really matter because ultimately we have to reach here. So yeah, doesn't really matter. So we are at here. From this position we really need to store our S and D. But we need to consider this guy first. So let's say that we have two variables, even and odd, okay, and we'll check that if the last element is even or odd. So the last element is even, so we'll consider the index of that, which is 4 in the even variable. and the odd variable will simply be -1. Nothing is there. Okay, so now we'll start from index 3, like the second last index, and try to go backwards. Okay, so we are at index 3. The element at 3 is 3, which is like odd, and we need to know what is its next immediate, like same parity index. So for the same parity index, like this is odd, the next should be odd as well. And we like look at this, guys. So in here we don't have anything in the odd yet. So for this, the same parity would be -1. And for the different parity, like this is odd, we need an even. We look at this, guys, and we really have an even guy. So we just copy that index and store it here. So for third index, S and D, we have S and D. We have our S and D. So now let's move to the second index here, and also we need to update our E and O as and when we cross that index. So here the value was 3, so it was odd, and the index of that is 3. Yeah, so we have 4 and 3. So we are here. What is S? What is D? So we want same parity. This is odd. We go to here, check, odd index is 3. So we simply put it like that. And we want a different parity. That is, this is odd. We want even. So it is at 4. So yeah, for this guy, the next immediate index J, which has the different parity, is 4, like the fourth index. Okay, and we update our E and O. This would be 1 again. Sorry, 2. The index of this guy. So E is 4 and O is 2. Now we are at this position. Okay, so here the S would be, yeah, so the same parity, like 2 and 2. So 2 is even and this guy is 4, and the different parity, even and odd, so this guy is 2. As we can see that the next immediate index for this guy for the same parity is 4, and the next immediate index where we have different parity is 2, this guy. So this would be our basically an array. This will be 2 arrays basically, and let me call it J1 for this I and J2 for this array. So these are our 2 arrays which we will pass to our DP function. Yeah, so there is one more thing that we need to consider here, is that we are given in the problem statement that jump2 can only be used at most once. We cannot use more than 1. Okay, so now let's formulate the DP recursion. Okay, let's say that we have a function where we have the first state as the I, where I represents that we are at the position I. Then let's say the second state would be U, where U says that whether the jump2 has been used or not. And J1 and J2 are arrays. So these are the arrays basically which we have pre-computed them. Okay. So the base case would be that, if we have reached the nth index, we would simply return 0. Okay. Yeah. So now let's say that let's define our answer as some max value, which we will eventually return that. Right. So now we have 2 possible values for U. Like you could either be 1 or you could either be 0. right? So let's say that u is 0. What does it mean? Like, let's say u is 1. What does that mean? That means that we have used jump 2 already, so we cannot use now. We just have to use jump 1. Okay, so let's use that. And also we need to consider that, like, if the index at the j1i is not -1, then only we need to proceed further, because it could be the case that the value at j1 array, the value in the j1 array could be -1. So like, there cannot be any further element which has same parity. Like in this case, there was this 3 and it did not have any same parity, so that's why it was -1. Okay, so if it is not -1, then only we proceed further and find our optimal answer. So answer is equal to nothing but the minimum of answer comma. Now you do the recursion. So this would be, so from I we are going to jump to j1 of I, and the state for u, the value for u would be 0 itself, because 1 itself, because we have already used j2, right? Okay, and j1 and j2, so plus 1 we need to add, because we are considering this, we are taking one step from I to j1 of I, so that's why this 1 plus 1. Okay, and in the else part, when u was 0, like else is when u is 0, right? U is basically 0. So we have again like two choices in here. We can use either jump 1 or jump 2. So we'll try both of them. Like, okay, so and again, if the value at j1 of I is not equal to -1, then only like get the answer. So here we are considering j1, like same parity, right? So j1 of I, and the state for u would be 0, because we are not yet starting the j2. j1 comma j2 plus 1, and the second case would be if j2 of I is not equal to -1, then let me just so answer would be, if not equal to answer would be answer comma function. Well, here we jump to j2 of I, right? And the state would now become 1, so we have used j2 now, and j1 comma j2 plus 1. So after that, after everything is done, we just return the answer. Okay, so that's the DP form, recursion for the solution, and we can then use memoization, like DP memoization. So like we're given that n is less than equal to 10 to the power 4, so we can have a DP state like something like that. And for this, the first would be for this I, and the second for u, like we just have two possible values, 0 and 1, so here it would be 2, and then we can simply store our answer into this, right, and formulate our DP memoization solution. So yeah, I hope the solution was clear enough, and the code is in the description. Go ahead and check it out. Thank you so much.